In this video, I'm going to cover how we solve real-world problems by solving first-order differential equations. And the example in this video is going to cover Newton's law of cooling. Okay, and in Newton's law of cooling, basically says that, let me go here, okay, that a change in temperature, okay, is proportional to the temperature difference between the ambient temperature, TA, this is going to be a constant, we're going to assume it to be a constant here, and the temperature of the thing that's being cooled. Okay, so the change in temperature is proportional to, equals K times, the difference between the temperature in the ambient environment and the temperature of the thing that's being cooled. Okay, great. So how can we solve this kind of differential equation? Well, I'm going to show you that there's two ways to do this. The first way is separation of variables. Okay, the second way is to use the integrating factor method. Both techniques will result in the same solution. Most problems will have, some constant temperature given to you. Most initial values will give you this proportionality constant, and because we have to integrate these types of differential equations, we'll also need another data point for the undetermined coefficient, the c's in our integration, because that's how we solve first order differential equations. Okay, so what I'm going to give you is sort of a general solution. I'm not going to give you actual values in this video. I'm just going to tell you, the ambient temperature, proportionality constant K, and what I'm going to do is I'm just going to show you that they can be solved, okay, using these two techniques. Okay, first, let's cover separation of variables. This is pretty quick and easy. So number one, change pen, separation of bars. Okay, cool. What are we going to do? So dt by dt is k ta minus t. What do we have to separate? We have to separate the temperature and the time. Those are the two variables. Okay? So if you're used to x and y, here, let me map it for you. So y is going to be our temperature. Okay, clean that up a little bit here. Y is going to t, okay, and the x's are going to time. Okay, this is the mapping, and you're used to dy by dx. Usually is k times some constant. Here, I'll just make a constant. That's why you probably more comfortable working with x and y, but anyway, we're going to work with t and lowercase t here. So that's where we're okay. So let me clean that up for a second here. Okay, so what do we want to do? We want to separate the variables. Well, we got to keep everything in these brackets together in order to do that, because the t that we're looking for is here. So what we're going to do, we're going to divide both sides by the TA, which is a constant, minus t. So we're going to go 1 over TA minus t, and we have our dt is equal to k, and then we're going to multiply both sides by dt. Okay? Let's see. How does that help us? Sorry about that. Okay, so we've now separated the variables. We've got TA minus t. We've got the t's on one side, the uppercase temperatures, and lowercase t is time. So now we can integrate both sides. K is a constant, so I can pull it out of the integral. In order to solve via separation of variables here. In order to solve the left-hand side of the equation, we need to do a u substitution. Okay, where u is equal to TA minus the temperature. Okay, so TA is a constant. So if u is this, then what is the derivative of u with respect to temperature? Well, TA is a constant, so that's going to go to 0. And negative t by dt is -1. And so du is negative dt. Okay. Now, when we look at our equation, we have a dt here. We have a negative dt here. So what we need to do is we need to put the negative here and there. Okay, so we have a positive dt now, and that is going to be replaced with a negative du. Okay, so remember, in u sub, whatever's on, we look for what's on the right-hand side in our equation, and we replace it with what's on the left. We look for what's on the right-hand side, and we replace it with what's on the left. Okay, so this becomes the integral of 1 over u, and it's negative du. And that equals k dt. Well, that's just k t plus some constant. I'm going to make it 2, because I know that I'm going to get an integral right now from the left-hand side. So what am I going to get? I'm going to get, this is the integral of 1 over u du is ln u. So I have negative ln of u plus some constant is equal to kt. I'm going to call this constant 1, kt plus k c2. Great, I've got constants all over that I can group together. Okay, so let me do that. Actually, before I do that, I can do it either way. It doesn't really matter. I'm going to go negative. Let me plug back in the u. So ln of TA minus t equal to, okay, kt plus, I'm going to call this C naught. Okay, when I group the C1 and KC2, I'm going to lump them into a C naught. Literally, C naught is equal to K C2 minus C1, if you're looking for that. Okay, now if I multiply both sides by -1, then I have ln TA minus t is equal to negative KT minus C naught. Well, here, let me introduce a regular C. So this becomes ln TA minus t equals negative KT plus C. Okay. Now I can leave it like this. Okay, so leaving it like this is one option. Okay. Or I can solve for TA minus t. I'm gonna have this as one potential solution. So this is in ln form. But if you want, you can convert. So you say TA minus t is equal to e to the negative kt plus some constant. Okay. So what that means, okay, so TA minus t equals e to the negative kt times e to the c. Well, that's just a constant. Okay, so we can call this, pick another constant, I don't know, we'll call it C3 for now. Okay, so that means that TA minus t equals C3 e to the negative kt. Okay, and so what we can do is we can bring t to the right hand side, or we can here, we can just, let me just do it in a way that makes it easier. So we got negative TA plus C3 e to the negative kt, okay? And then if I multiply both sides by -1, then this becomes negative, okay? And so what we have is we have our next, the solution in a nice, T is a function of time. T is always, temperature is always a function of time here, is the ambient temperature minus C3, or we can now change it. It doesn't have to be C3. We can just leave it. It's just a constant, okay? C e to the negative kt. Okay, so this becomes the solution, you know, when you solve for T directly, okay? Turns out that the ln form, it's good to solve for time. If you do that, if you're trying to solve for time, it's better to leave it in ln form. Less steps. Okay, so this is the other form. So these are the solutions you get via separation of variables. Okay, and it requires a u substitution in order to make this work. Okay, how do you solve the same differential equation using the integrating factor method? And that's what we're going to do next. So number 2, I'm going to zoom in a little bit. So we're going to say here, integrating factor. And basically what I'm going to show you, okay, is that the solutions are the same regardless of the steps. And in real problems, you'll know they'll give you TA, that's the temperature, right? They'll give you the initial conditions. And then you can solve for CK using the initial conditions, okay? All right, so the integrating factor. So what I'm going to do is I'm going to take the same problem. This is our initial problem. I'm going to copy it, bring it down here, and then I'm going to paste it right over here. And we're going to solve this using the integrating factor method. In the integrating factor method, let me zoom in here. Basically, we have to have it in a certain form. Okay, let's convert it to the form that we need to have it in for the integrating factor method. That's, if you remember, we use y and x, but we have, if you look up here, we have T and temperature and time. So I'm going to put it in that form. So here, let me zoom in just to make things easy. Okay, so what we remember y and x is dy by dx plus p of x y equals q of x. Okay, and we have to multiply both sides of the equation by the integrating factor, which will collapse the left-hand side to look like product rule. And we saw this in the derivation. So this is e to the p of x dx. And then when you do that, you see this, the left-hand side of our equation looks like product rule. It becomes y r by dx, and we're just multiplying both sides by r of x. So we have q of x already on the right hand side over here times r of x. Okay, and then you can solve dy r q of x r of x dx, and then you can integrate both sides. Okay, that's just to remind you of the integrating factor method. Now, to do this in this form, first off, we got to put it in this form. So let's take our equation here and put it in that form. We have d temperature by d time is equal to k TA minus k times the temperature. And so we're going to take this kt and bring it over to the left-hand side. Okay, so we've done that. And now we can identify, okay, we can identify this guy right here. See right here? That's our p of x. Well, we're using t. So this is p of t. And that means that this guy right here is our q of t. Okay? So that's basically what we have. K times TA is just some constant. It really doesn't matter. So we're going to follow along. So we have a differential equation, okay, where we have, if we were to multiply both sides by r of t, now not r of x, we're going to use r of t, then in order for it to collapse to this expression here, we have to find out what is r of t. Okay, so let me just to make things nice and to align things up for you here, I'm going to put same solution here. So I'm going to convert what we have here. So we're going from y goes to t, okay, right, and x goes to lowercase t, okay. All right, so our expressions, we have r of t now is equal to e to the integral of p of t dt, right, because x went to t, and the solution form is right over here. We can write it this way if you like. So we're going to say integral. Actually, here, let me just quickly. What's the integral of dyr? It's just yr. Okay, so I don't have to do that on that side. So let me go back here. So let's go back here. Y went to t, so this became t times r. Okay, both are functions of time, is equal to the integral of q of t r of t dt. Well, what's q of t? It's a constant, right? In this, q of t is k times ta. Great. So let's just put it here. K ta, that's our q of t. Our r of t, right, is right here. We don't know what that is yet, but this is just r of t. We're going to figure that out, and then dt. Okay, so we're going to solve this one now. So we need this expression. So let's keep these. This is just converted so that it lines up with what we have in our problem. Okay, so we are going to, number one, solve for r of t. Number two, sub it into the solution form and solve for t. Okay, cool. Let's do it. So r of t, what is r of t? It's e to the integral. What was p of t? Just k, right? And then dt. So this becomes e, right, to the k t. There's the plus c, but remember, if you recall, because r of t multiplies on both sides of this equation, the c will cancel out. So we can ignore that from the integral here. All right, so we've got r, we've got q, we're ready to solve. So we have, so that's 1 and 2, t of t. Okay, r of t is, here, why don't I just divide both sides by r? It's 1 over, in equation 2, I'm just going to bring r into the, here, why don't I just 1 over r of t, and I can just do that. So this is t. Here, let me just clean that up a bit for you. Okay, all right, so this becomes 1 over r of t. R of t is e to the kt. So here, e to the kt times the integral of, here, I'm going to bring kta, they're constants. So bring it out of the expression. And then e, so r of t is e to the kt dt. So we're almost done. We're almost done here. So what does that do? e, so k ta over e to the kt. The integral of e to the kt is 1 over k e to the kt plus some constant that we don't know. Okay, if we multiply through, we're basically left with ta plus, okay, c k ta and over e to the kt, or e to the negative kt. Awesome. This guy, right, all of these things right here, they're just constants. C0, let's call it, so then the solution, ambient temperature plus C naught e to the negative kt. Okay, let's compare that to what we have up here. We have a minus c, okay, but because it's an arbitrary constant, it could be a plus c, right? So what we could do is we could say let c equal negative c naught, right? Because it's an arbitrary constant. I'm just trying to show you that they're the same. And this expression is the direct solution that we found right here, okay? And we can, go backwards and show that it's the same as this one, but you can already see that, right? I derived this expression right here from this expression right here. So this one is exactly the same as the one we have here. So at the end of the day, regardless of the approach that you take, whether you use the integrating factor or if you use separation of variables, you're going to get the same solution. And basically, I'm going to take a copy of this form right here, bring it down here, okay, and just show you that you can get to, let me just paste it here, that it's the same thing as we have there. All right, let's do a real world problem from this. Again, let me clean that up. Okay. All right, so let's take a look at an example. So there's one in our notes. I'm going to zoom in here. The one in our notes says this. Okay, in our notes, we have an example with a coffee cup, okay? So we go to Tim Hortons, we get a coffee cup. The temperature when we get it, it's 150 Fahrenheit, okay? So 150 Fahrenheit when we get it, then after 2 minutes, we measure the temperature and it's 130 Fahrenheit, okay? They tell you that the ambient temperature, okay, is 70 Fahrenheit. Now, all of these are enough to solve for, okay, we got TA, K, and C. So we've got 3 data points. 3 data points, 3 unknowns, we can solve this. Okay, so let's solve for K and C. Well, the TA is not unknown anymore. So we're going to use these data points to solve for K and C. We're going to plug them in, and then we're going to isolate for the time. And then we'll, the question in this problem is, I want to drink my coffee at 110 Fahrenheit. So how much time, right? So T at 110 Fahrenheit, what is the time? How's that? I'll just write it like that. Okay. I'm waiting for the coffee to reach 110 Fahrenheit. How long is it going to take? Okay, from when I first picked up the coffee, because my time when I start at 0 is 150. Awesome. Let's figure it out. So we got these two equations. I prefer to use the ln form because that's just easier. So that's what I'm going to do. Okay, so I'm going to use number 2. That's the solution to the differential equation. So I'm going to go ln. And here I have TA minus T. So TA is 70 minus T is equal to negative KT plus C. Okay, so I'm gonna use my data points 1 and 2. So when time is 0, okay, so I'm gonna plug that in. I'm gonna use my I should call this A and B then. Okay, so we're gonna use data point B. Okay, T at 0 is 150 Fahrenheit, so ln 70 minus 150 is equal to negative K 0 plus C. Okay, right. So what do I have here is that this goes to 0, so C equals ln of negative 80. Okay, or we could okay, one important point. You see how the solution is the magnitude here? Okay, so we are always taking the magnitude. This is actually a very good point to make here. What's the magnitude of negative 80? Well, that's positive 80. Okay, so C is ln of 80. Okay, so let's sub that in to 2. So 2 becomes, let me just see it here, is ln TA minus T. We have the TA, sorry, I'm going to put that back in. This is an actual problem here. So 70 minus T is equal to negative KT, and C is ln 80. Okay, now to simplify this, I'm going to bring this ln over to the left-hand side, the ln 80. So what I have is ln 70 minus T ln 80 is negative KT. And if we remember our ln rules, ln of A minus ln of B is ln A over B. So what we have is we have ln 70 minus T over 80 equals negative KT. Awesome. We're making some good progress. Now what we need to do is we need to use the second data point. So we're done with the first one, or well, we've subbed in the 150, and that got us C. Now we got to sub in 130 when time equals 2 to get K. So what we need to do is sub in B. B. Okay. So now what we're going to do is we're going to say that when T equals 2, when time equals 2, temperature is 130. So this becomes ln 70 minus 130 over 80 is equal to negative K, and time is 2. Now we can solve for K. So what does that become? So if we, what we can do is we can say that negative K equals 1 over 2 ln of 70 minus 130. Oh, 70 minus 130 is 60. So let's do that. This becomes 60 over 80. Okay. Right. Okay. Let's just make sure we got all the stuff here. Okay, 60 over 80 is like 3 over 4. Okay. So what does that mean? That means that K Okay, or let's say 2k equals negative ln of 3 over 4, right? And I just brought the 2 over. The reason why I'm doing this is that I want to flip this 3 over 4 because you don't want a negative ln. So let's, or we can probably, you know what? I want to keep things nice and simple. So a ln b is ln of b to the a, right? So this is negative 1. This is, so 2k is equal to ln of 3 over 4 to the negative 1, okay, which is just 4 over 3. Okay, and that means the k is 1/2 ln 4 over 3. Okay. Great, awesome. Let's take that and plug that into our formula here. Okay, so 2 becomes now ln 70 minus t over 80 equals negative, oh, you know what? I could have just used this. Negative k is right there. So why don't I just do that? I'll just use this negative k because I'm subbing it in to there. So I could just say, instead of that, I could just say 1 over 2 ln 3 over 4 times t. Right? Negative k is 1/2 ln 3 over 4. Okay. That works well. Okay, so now we just have to figure out, now we have our expression. We're not looking for the temperature, we're looking for the time when it reaches 110 degrees. So in this case, we need to solve for t. So let's solve for t. So t equals, I'm going to multiply the left-hand side by 2, so that's 2. Divide by ln of 3 over 4, and then multiply, oops, eraser is, okay, and then multiply by ln of 70 minus t over 80. So let's look at the time. How long does it take? So we want to reach, what was the question? What was it, 110 degrees? How long, what is the time when the temperature falls to 110 degrees? So let's do that. So let's plug it in. T equals 2 over ln of 3 over 4 times ln of 70 minus 110, 80. 70 minus 110 is like negative 40. Take the magnitude, it's like ln of 1/2. So this becomes 2 over ln of 3 over 4. And if you plug that into your calculator, you get about 4.82, and we're looking at minutes. So you got to wait about 4.82 minutes from when the coffee was poured in your cup for it to reach 110 Fahrenheit. Okay, hope you enjoyed this example, and we'll see you next time in math class.